learned earlier that allosteric is Greek, everything's from Greek, right? They invented everything pretty much. And it means others, referring to another site. So I really am not a big fan of referring to ATCase and the ligand binding as allosteric. I'd rather just refer to that as cooperative ligand binding. And so today we're going to really dig deeply into what it means for a enzyme to bind to its ligand with cooperativity, and more importantly, what are the biological implications of that? So in our study of biochemistry, we're going to concern ourselves with, first and foremost, the mechanism of cooperativity. How do enzymes like that one right there bind to a ligand cooperatively? Meaning that binding of the ligand, well, first off, let me say that the enzyme will exist in two different conformations. One of those conformations will have weak affinity for the substrate, which I'm using interchangeably with the word ligand, versus high affinity for the substrate. We refer to those as the T-state conformations and the R-state conformations. So we're concerned with understanding at the molecular level how the enzyme does that, right? And so that's one of the most important things that we're going to address. We're also interested as biochemists in how do we test our hypothesis. So we can make these observations, right? But what can we actually do to test our hypothesis? And this is the experiment that we've been talking about. We'll talk about in great detail today with this transition state analog, which is called PALA, P-A-L-A. And how can we use PALA to show that this cooperative ligand binding model really is true? And then last, and certainly not least, and the whole point of doing all this is to understand ultimately the molecular physiology, which is why is cooperative ligand binding a thing? There must be some biological advantage to it, right? And so we've been kind of discussing this where we talk about how enzymes that are cooperative in terms of their ligand binding, they can respond over a shorter range of substrate concentration. And so I think most of you understand and believe that now. So what I want to work on today is a little bit more of an intuition of why that is a biological advantage. That's something I've been thinking about a lot these days as we've been going through this. Now, as promised, I brought my laptop so we could actually look at the structure of these things. Honestly, I wish we had way more time for doing these things because it's my belief that this will be far more helpful to all of you than staring at ribbon diagrams on a page. Before we get started, what's your preference? Black background or white background? What do you think is easier? Black. Oh, you don't even want to see white and see what it looks like? Okay. All right, so what I'm showing you right here is the heterododecamer of ATCase. Remember, ATCase is in a ligament. We knew it almost had to be in a ligament, right? To have cooperative ligand binding, you have to have multiple active sites. And while we can envision a scenario where all of those active sites exist in one long polypeptide chain, it's far more typical that we'll observe multiple subunits, okay? And we also know now that ATCase has catalytic subunits and regulatory subunits. A catalytic subunit is going to bind to our substrates and catalyze the reaction by binding most tightly to the transition state conformation, as enzymes do. And then the regulatory subunit is going to bind effector molecules like CTP. And that is going to ultimately affect the conformation of the enzyme. So let's go over this now. So what you're looking at here are 3 identical copies of the catalytic domain in magenta. Sorry for the poor resolution. It looks great on my screen. But so this is one copy, this is another one, and this is another one. I think you guys can see, if you look at it, you can kind of see the hint of that symmetry there, right? But if you need help with that, typically what I'll do is I'll just look for a defining feature that's present. Let's see, can I find one? This long helix is pretty defining. Look at that sucker, super long. So that helix is identical to this one and this one. So you can really see it making this triangle, right? And so if I were to rotate this subunit 120 degrees about an axis going through the board, then this subunit would be totally identical and superimposed onto this one. And then if I go another 120 degrees, I'll get to there. All right, so that's 3 of the 6 catalytic domains. Where are the other ones? The other ones are on the other side. So let's flip this thing around. And there they are, now in green. Okay, so again, I have 3 identical subunits that are related by a 3-fold axis of symmetry. So let's maybe now show you guys I like referring to this as a catalytic sandwich, right? And so here's one, and that contains our 3 copies of the catalytic subunit, and then here's another one. All right, so what's holding these 2 things together? Right, they're not really touching one another. I mean, it might kind of look like there might be some interactions here and there, but for the most part, the 3 subunits, catalytic subunits in green, are not in contact with the magenta ones. So what's holding this thing together? That's the regulatory subunits. And so the regulatory subunits are painted either light blue or yellow, and you can see that this yellow regulatory subunit is making contacts with this catalytic subunit. It forms a homodimer with the blue one, and that blue one is in contact with a catalytic subunit in the green ring, right? So you can kind of think of, the homodimers of regulatory subunits as staples holding the 2 trimers together. Yes?
What's the PDB code for that?
Oh boy, that's a very fancy question. I believe it is 1RAI. All right, so let's kind of look at how the regulatory subunit is formed and how it's promoting the interaction of these 2 catalytic trimeric rings. Yeah, so I've got this yellow subunit and it's touching here, and it homodimerizes with the blue subunit, which is now touching this green subunit here. Interestingly, I never even noticed this until now, but look at the nature of the interaction of those 2 regulatory subunits. Is there anyone who might make a comment on speculating on how the interaction or how homodimerization is stabilized? It seems really clear to me right now. Yes? I like that answer. That's a very general, that's a very general description that could be applicable to almost any intermolecular protein-protein interaction. So that was good. I'm thinking of something a little more specific, and so I've got my man, I want to say Tyler Amos. That's who you are. You're way back there. It's hard to see you. Yes. So Tyler nailed it. He's saying, look at this. These regulatory subunits both have beta sheets. By the way, is this parallel or anti-parallel? Can anyone tell? Anti-parallel. Very good. And so you can see that really they're just forming a continuous sheet. So we go from having maybe, looks like 5 strands. Let me see if I can kind of, there we go. Twist this around so you guys can see that now we just have this long 10-stranded data sheet. I don't know if you guys remember this, but the book had talked about that, how that's a very logical way of forming a protein-protein interaction, because the interaction of those strands on the edges will now have hydrogen bonding partners. So instead of hydrogen bonding to water when they're separated, now they can actually hydrogen bond to each other. And no doubt there are side chains that are forming multiple weak force interactions stabilizing that homodimer. Okay, right, so now I think it's very clear to see how this thing is put together. So then the first major question we want to ask is, well, first of all, what is this state? What conformation of this? And so if this was crystallized in the presence of the allosteric effector CTP, which is a negative effector, what would be the conformation of this enzyme? It would be in the T state. Very good. You guys are on a roll today. And so I want to compare that to the conformation of the R state, right? How am I going to do that? That's right. Crystallize the structure of the heterododecamer in the presence of pala. Why does that work? Why does crystallizing this with pala work?
The pala is close to the transition state, so
Right.
So when it makes interaction with the protein, it's kind of in our state.
Beautiful. That's exactly right. So, yeah, Rebecca?
What exactly do you mean by crystallizing?
Well, I mean, that's how we determine the structures of proteins and macromolecules in general. Is we purify them, and then we grow little crystals,
Okay, so
and then
you
we
do the
shoot
actual
them
process.
with X-rays.
Okay.
Yeah. Yeah, so pala is a transition state analog. And so enzymes are evolved to bind most tightly to the transition state. And we know that in the presence of substrate or the transition state, this enzyme will prefer to be in the R state conformation. Now that's one of the things we want to address in class today, is can we use these structures to understand, can we understand why the T state has weaker affinity than the R state using these structures? So let's now go ahead and put that structure up. And that's going to be in gray. And what I'm going to do is I'm going to turn off some of the subunits to make it a little easier to see. Now I have to do something to help. You can see everything. So basically I've got now the superposition of two structures of ATCase. One was ATCase in the absence of substrate, in the absence of pala, but in the presence of CTP, and the other is now in the presence of pala. So what I did is I used the catalytic domain shown in green as the basis of superimposing those two structures. Remember, the green one is the T state. The magenta one is the T state. And then everything in gray are the corresponding domains in subunits for ATCase in the R state. So I told the computer that I wanted it to superimpose based off of this catalytic subunit. I think you can see they match quite well, but it's not perfect, right? If we zoom in, you can see that there's changes in the positions of these loops here. So even though I'm telling the computer to superimpose based off of this catalytic subunit, we see that there are changes. But when we zoom out, you see that there are even larger changes occurring, right? Where now the position of the magenta subunit is very different than the position of the gray one for this different subunit in the heterododecamer. And so what we see is that this enzyme has really grown. It's always like jaws, right, that have opened up. The gray one has moved up relative to the positions of this regulatory subunit and this catalytic subunit. You guys see that? Is that clear to everybody? All right, so that's what they mean by conformational changes, right? That the structures have fundamentally changed at the level of both tertiary structure and quaternary structure. Now, what I want to address is what does substrate binding look like, right, in these two very, very different structures. And so now what I'm going to do is I'm going to turn on Pala. Okay, we're going to have to really zoom in. So Pala is now shown here in yellow. It's kind of hidden, right? And so I need to try to make it a little easier on us to figure out what the binding looks like. But the first thing I just want to show you guys is, the first thing I did when I looked at these structures is I asked myself, how is this thing even going to get into the active site, right? Where is the opening of the active site? We've discussed that kind of a lot, right? We really got into it in chapter 8, and to some extent we talked about it in chapter 9. Clearly you can see there's a hole right there. And that's where the access to substrate is going to be. That's how substrate can bind to the active site, is by entering the active site through this little doorway, this molecular doorway. And that's how product is going to dissociate off, is leaving through that doorway. And so what I want to do now is make some atoms go away so that it's a little easier to see. That's better, huh? Now we can really just get in there. And so Pala is going to be down to the R state. So first thing, I'm going to get rid of the ribbon diagrams. And now I want to show you all the atoms, because now we really want to scrutinize how is this thing stabilized? What are the weak force interactions between Pala and the proteins? Now I'm going to turn on the structure of the R state conformation. And now we're seeing, even though I'm not coloring the individual atoms, I think that we could use our intuition to figure out what these residues are. For example, Pala has a phosphate group right here. So if I click on that, you can see that that was the phosphorus atom. That's what the program is telling me right there. So these are all going to be oxygen atoms. See that, O1, O2, O3. And so what kind of residues would you expect to be in the active site stabilizing the transition state conformation near that phosphate base? Positively charged, so let's get some real residue names here. Someone said lysine. Arginine, okay. Well, what do you guys think this thing is? It's arginine. There it is, Arg54. What is this thing? That's also an arginine. Someone had said lysine. Are there any lysines around here? Oh, I know there's one in here. I saw it like this morning. I mean, here's a histidine. That's positively charged too, yeah? What is this guy? That's another arginine. I mean, this thing is just decorated, right, with these positively charged. I don't see my lysine, but that's okay. I can deal with that. Yeah, so what we see by looking at where the atoms are in the active site are weak force interactions, salt bridges stabilizing the interaction with Pala. You can really just see that They just look like they were made for one another. And then again, this is going to be how the substrate and product get on and off of the enzyme through that molecular gateway. Now what I want to do is I want to turn off the structure of the ATCase catalytic domain that's in the R state conformation and now show you what it would look like if the T state conformation is there. So I want you to keep in mind that Hala wasn't present in that crystal structure. I'm just keeping it around from the crystal structure of ATCase in the R state conformation. So we'll lose that and we'll bring that in. Holy smokes. All right, so number one, can you guys see there's some problems? Like all those atoms are hitting one another. So clearly this Hala cannot exist in this active site, in this conformation at least, right? Because we know that two different atoms cannot occupy the same physical space. Another thing that immediately jumps out at me is that molecular gateway that I was just showing you, I'll put it up again, is totally gone, right? So there was this beautiful hole right here, and it's to a large extent now closed. So once again, let's just get rid of the red atom. So this is the R state. Here is our gateway, enabling substrate binding. Now, if I ditch it and I put the T state conformation in, that gateway is so much smaller, right? So it would be much, much harder for substrate to bind, and then the active site is also not in a great conformation for actually even enabling this, right? So we can really see in these structures that everything that we've been talking about in class is true in this example. Why is the T-state conformation weak in affinity for substrate? Because it has this extremely small, narrow gateway enabling substrate binding that allows the substrate to enter the active site. And once it gets in there, the active site is not really even configured appropriately anyways for high affinity binding. So maybe the substrate will get in there finally, and it will hang out for a little bit, but then it's going to leave because it's not forming those multiple weak force interactions that stabilize it that we observe in the R state conformation. Yeah. Okay, then I want to show one more thing. Let's now get rid of the color. I want to look at what's going on with CTP, because even though we haven't really talked about it yet, we're going to talk about it quite a bit today. CTP is a negative allosteric effector of ATCase. And so how does that work? I mean, CTP binding does not occur at the active site. So everything we just talked about can't really be the mechanism. There's got to be a distinct mechanism. And that's where these regulatory domains are going to come into play. So you can see now that I've got in purple a CTP molecule. And that CTP molecule is now nicely bound in between these loops in the regulatory subunit shown here in light blue. And so that's just this beautiful little, I don't know how to describe it. It's this delicious molecular interaction that's stabilizing that conformation. It's like basically taking something that is already kind of stable and shoving a block in it to stabilize it even more. I mean, it's kind of like this. It's kind of like if I'm going like this, and my arms are changing conformation, and Matthew comes in, he's like obviously way stronger than me, and he holds my arms out like that, that would be a stabilizing interaction. And that's what CTP is doing. It's just jamming itself into this regulatory subunit, and once it's there, it makes it much, much more difficult for the conformation to change. For the conformation to change to the R state, basically this thing needs to get out of there. Let me show you why. Now let's turn on the structure of a ribbon diagram of ATCase in the R state conformation. Look at how different that is. Let's zoom in. I mean, I think you can see that the binding site has totally changed. With the position of those loops in beta strands, those things that are stabilizing the interaction with CTP have totally moved. So effectively, the R state conformation is disrupting the CTP binding sites, no longer even there, right? So the R state conformation is going to do two things. It's going to open up the gateway, allowing substrate to bind, and present an active site that is conducive to transition state formation, and it's going to block formation of the CTP binding site. Okay, you guys get it? Was that amazing? Good. No, I'm not seeing like a lot of smiling or anything, but I'm tired too, actually, so I get it. We actually can't because I only have 45 minutes now. So I can tell you about it at office hours if you're coming, or sorry. Okay. That's chapter 15. I mean, Lana, we're still going to kind of review this stuff, by the way, so maybe you'll get what you need on the slides. So this is where we left off on Thursday. We were talking about ATCase and the two different conformations that it existed. We acknowledged that in the absence of substrate, or I should actually rephrase that now, say it in a bit more of a savvy way. In the absence of a high enough concentration of substrate that can actually bind to the enzyme is going to overwhelmingly be favored in the T-state conformation. Your book says the equilibrium constant is 1/200 for this conformational change reaction. And so ultimately, what's going to happen is that in the absence of regulators, in the absence of PALA or CTP, or as we'll see, ATP is a positive effector, in the absence of those molecules, it's going to come down to substrate binding to change this equilibrium. And now, hopefully, with our little presentation, you guys can appreciate better how that's going to work. Because even though the T-state has poor affinity for substrate, eventually substrate will bind to one of those active sites. And when it does, the enzyme now is going to be more energetically favorable in the conformation that we call the R-state conformation. So by substrate getting into that active site, it's going to stabilize the R-state conformation, changing this equilibrium so that it's going to be the opposite. So hold on a second. 159 pages. Why? Do you guys think like if I tried to sell like those notebooks on Amazon, I could make like $1 million? No. No hurts to try. And then again, not no substrate. I need to rephrase this to say the substrate concentration is low relative to the affinity, which we are now using interchangeably with KD, the equilibrium constant for binding. Substrate concentration is low relative to the affinity of substrate for ATCase in the T-state conformation. Let's just refer to that now as ATCase T. I'm going to draw my equilibrium arrows to reflect that. Now we're going to imagine a scenario where the substrate concentration is high enough to start binding. The substrate is now high enough to partially bind to ATCase. Now we can imagine a couple of different ways this is going to work. I mean, number one, if my T to R equilibrium over here dramatically favors the T state, it does mean occasionally I'll have an R state around, right? And so that R state can bind to substrate, right? And then we also acknowledge that even when the substrate concentration is relatively low, it will eventually bind to the T state. So there's going to be this sweet spot where substrate starts having an effect, where it can start binding to the enzyme, both enzyme that's in the R state, even though that's going to be relatively minor fraction of the population of enzymes, and the majority will be enzymes in the T state. So now we're going to say substrate is now high enough to partially bind to ATCase in the T state, and now our equilibrium is totally changed. And that's in effect how cooperative substrate binding, cooperative ligand binding works. Right? The substrate concentration needs to get high enough to where it starts binding to enzyme. But once it does, it has a dramatic effect on the equilibrium of the conformation of ATCase, shifting that equilibrium from being more favorable in the T state to being more stable and favorable in the R state. Once it's more favorable in the R state, all of those active sites are going to become filled up with substrate upon only very minor increases in substrate concentration. All right, so this forms the what's the right word? I'm tired too. So this is going to be the key slide that takes everything home for us. So I really want to spend some time talking about this. By the way, for those of you with 9th edition books, for some reason, the authors decided to leave this question out. It's in your syllabus though, okay? So that's where you're gonna find this. For those of you with the 8th edition, you're good to go. And basically, it's a question that talks about PALA, and we know what it is. It's a potent inhibitor of ATCase that binds to the active site and induces the R state conformation. And so there's this conundrum where we observe that adding PALA to ATCase in the presence of substrate will actually result in an increase in product formation, or an increase in catalysis, which is kind of bizarre. Then it says until an average of 3 PALA molecules are bound per enzyme, and then eventually it says at higher concentrations of PALA, the reaction rate quickly decreases and goes to 0. And so the question is, how do we explain this? And so the options are PALA stabilizes the R state at low concentrations. We know that's true because PALA is a transition state analog, and those things will have potent binding affinity for an enzyme. Enzymes that contain 3 or less bound PALA will have higher affinity for the substrates in the unoccupied binding sites. That's also true, because the binding of pala even to one of those 6 active sites in an ATCase heterododecamer will change the conformation to the R state. And now, those 5 active sites will display high affinity binding for substrate. So that's why that's true. Enzymes that contain 1, 2, or 3 pala will now be in the R state, and as such, their affinities will increase for substrate. Higher concentrations of pala will block all binding sites. Of course, because eventually, if we add, pala is a potent competitive inhibitor. As we learned in chapter 8, the only way to overcome a competitive inhibitor is to jack up the substrate concentration. But if you jack up instead the inhibitor concentration, then obviously the inhibitor is going to saturate the enzyme and the substrate doesn't have a chance. So the correct answer here is, of course, all the above. But in my opinion, this is still a bit unsatisfactory. So what I want to work with you guys on today is how would we set up this experiment in the lab? That's what we're going to discuss right now. It's exciting. All right, so we'll call this the ATCase pala experiment. And what I want to observe, I want to observe an increase in V naught upon addition of pala to a solution containing ATCase and substrates. But the question then I have for you, what should the substrate concentration be? And what should the pala concentration be? Now, does anyone have any ideas before we get into it on how this would work? Yeah, Natalia.
1 to 2 because pala binds 2 active sites.
So you want me to use a molar ratio of
1 pala
1 to 2?
1 pala to 2 substrate.
2 to 1.
Yeah, sorry.
Okay, that's an idea. Anybody agree with that? Want to change it? Disagree with it? Want it?
I believe it is noticed the substrate concentration like Frank said is higher than
So now Alana is adding some stuff here. She said, she wants the substrate concentration to be higher than the KD for what? You can't just say KD though, you have to tell me the KD of what for what? The KD of substrate for, but you have to tell me which conformation. Okay, so you think it should be the R state. Very good. So if the substrate concentration is higher than the KD of ATCase in the R state, then what's going to happen? It means that when the enzyme is in the R state conformation, the substrate will bind. So Lana is right. And that actually adds major value. I don't have a problem with what Natalia was saying, but we want to try to add more understanding to this. And you can't really talk about molar ratios of these things until we invoke affinities of pala for the enzyme and substrate for the enzyme. So Alana wants us to have the substrate concentration be greater than the KD of substrate for ATCase in the R state. But what about with respect to the KD in the T state? Do we need to think about that too? Question about that. The answer is yes, we absolutely have to think about this, because if the concentration of substrate is chosen such that it is much greater than the KD of ATCase in the T state, then it will bind. And we don't need PALA to do anything then. Right? The whole point of this experiment is to have two different conditions: to run the reaction and measure the velocity of that reaction in the absence of PALA, and then do it all over again in the presence of PALA, where we get the amounts of everything correct such that our initial velocity jumps up, I believe they say 17-fold in their example. So there's a huge change in the initial velocity upon introducing PALA. So do you guys get my point that if I chose a substrate concentration that was greater than the KD of substrate for ATCase in the T state conformation, then I wouldn't need PALA at all. So let's write that, and then put a big X by there to imply that we can't have the substrate concentration be that high. It needs to be less than the affinity of substrate for ATCase in the T state conformation. We don't really want substrate binding appreciably to the enzyme when it's in the T state conformation. We want PALA to change the conformation from T state to R state. And then all of a sudden, that's when we want to observe substrate binding. You got it? Okay. So instead, we're going to say we want it to be below the KD for ATCase in the T state conformation. All right, so now we just have to talk about PALA. And so how do I set the PALA concentration, guys? You guys are doing so good today. Maybe it's the anticipation that we might see rain for the first time in 20 years. What should my PALA concentration be? I'm gonna let someone else answer. You guys have already done so well. Yeah.
Has to be greater than the KD of T state, so it can change.
I know your name. It starts with an H. Hassan?
Yeah.
Right, okay.
Yeah, so it has to be greater, so the substrate concentration has to be greater than the KD of the T state, so it can.
We're talking about PALA, so don't say substrate.
Oh, no, sorry, yeah, so I was just.
Oh, it's okay.
So, yeah, the PALA has to be, so the concentration of PALA has to be greater than the KD of the T state, so it can change the concentration.
Excellent. Let me ask you, and that's fine. So let me ask a different question. What should the concentration of PALA be relative to the concentration of the enzyme? And I'm going to drive here because you guys can see it gets complicated because we're dealing with the affinity of substrate for two different conformations of the enzyme that have distinct affinities. And now we have to worry about the affinity of PALA for the enzyme. And we have to ensure that PALA concentration is sufficient to bind and not to saturate. And so there is some value for the KD of PALA for ATCase that would fulfill this. We don't need to worry about that though. That's beyond the level of this class. So all I want you guys to take home are these three key points. To get this experiment to work, we need to worry about the relative concentrations of all the different components of the reaction. The enzyme, the substrates, and PALA. Specifically, we need to make sure that the substrate concentration is going to be significantly greater than the KD of substrate for ATCase when ATCase is in the R state conformation, because that's how substrate binding is going to occur. If this first point, let's call that point number 1 maybe. This is point number 1. If this wasn't true, then substrate would never bind, and we'd never get product. And then in the second point, we acknowledge that the substrate concentration has to be significantly lower than the affinity of substrate for ATCase when it is in the T state conformation, because we don't want substrate to drive the cooperative ligand binding on its own. We want pala to do that. So that's why the concentration of substrate is significantly below the KD of substrate for ATCase in the T state conformation. And then, last but not least, in the third point, we're just going to add sufficient amounts of pala to occupy 1, 2, or 3 active sites on average in our population of ATCase molecules, enabling some active sites to be empty, such that those enzymes that are bound to pala will be in the R state conformation, such that point 1 will now hold, and the substrate concentration will now be sufficient to drive binding of substrate to the enzyme, enabling catalysis of the reaction and product formation. Ta-da! All right, so I need to move on. If there are any questions, now would be a good time to ask. On the other hand, if you need some time to let this simmer, you can come on Wednesday. I don't know if you saw the announcement that I made, but this covers the last challenging topic, e.g. testing topic, that I wanted to go over with everybody. And so on Wednesday, I will be on Zoom, same time, same place, but I have no plan. You guys are in charge, okay? You guys are going to be the ones now who have figured out what's on the exam using the, in my opinion, like ridiculously easy techniques to figure out what's on the exam. And if there's anything that you want to go over, then you'll ask me questions. Yes, Rubon.
For the last condition for the pala, is it about binding to the T state of ATCase? Or
Yes, it is. You're right, because again, with pala, we want it to bind to the T state. We need to shift that conformation. That's very true. Yeah.
Generic question, are these 3 conditions true for every case of enzyme substrate binding in presence of some kind of inhibitor?
That's a really good question. That's a very curious question. I don't see why not. You know, as long as there are sufficient numbers of active sites, then I don't see why this wouldn't be doable. That doesn't mean it's true, though. I'm just speculating. But that's okay. All right, let's keep going now. And you know, and at this point, we've now beaten this to death, right? So the T and the R state explain cooperativity. And now what I want to do is I want to look at a graph that first kind of explains why do we get the black curve, the sigmoidal curve. That is the curve that we observe that shows the relationship between the initial velocity of an enzyme that displays cooperative ligand binding and the concentration of substrate. And what you can see is that is actually just a combination of, if we were to blend the portion of enzymes in our solution that are in the T state versus that are in the R state. So for instance, I'm going to look at 3 different scenarios. I'm going to look at this one right here. I'm going to look at this one right here, and then I'm going to look at this one right here. Let's do the easy ones first. So in this scenario, black line is still identical to the red line, right? Why? Because the substrate concentration is so low that the enzyme is not actually in the R state conformation really ever. So down here at really, really low substrate concentrations, our observed curve is identical for what we would observe for a non-cooperative enzyme that exhibits weak affinity binding to substrate. Similarly, if we look over here at scenario 2, say that the observed curve behaves exactly as the curve that would be observed for an enzyme that does not display cooperative ligand binding, but yet has high affinity binding to ligand. So that would be the R state curve. So at this point, all enzymes in our population are in the R state conformation. Over here, all enzymes are in the T state. So what's happening in the special case here where the black line diverges from the pure R state curve or the pure T state curve? Well, what we can see is that it's really just a blending. So what you have to imagine, again, is that we're observing a solution, guys, of hundreds of millions and trillions and billions of enzymes. So some of those enzymes, so this is going to be the substrate concentration that I want to talk about right now. Green. At that substrate concentration, if we have the ability to estimate the fraction of enzymes that are in the T state and the fraction of enzymes that are in the R state, what we would see is we would get fractions that correspond to the difference between here and here for the R state and here for the T state. I said that really poorly, so let me try that again. What I'm trying to say is that in situations where the observed curve for initial velocity versus substrate concentration diverges from the curves that would be expected for a non-cooperative enzyme, we can just imagine that in the population of enzymes in our solution, some of those enzymes will be in the T state and some of those enzymes will be in the R state. So there is a heterogeneous population. And that's ultimately what produces this S-shaped curve.
Would it be correct to say theta equals to half Emax?
You can't say that with cooperative enzymes. Another good point by Ilana. It's very tempting to want to talk about Michaelis-Menten kinetics constants because we know it so well and it can be very useful, like what Ilana just wanted to do. She wanted to talk about Km. She wanted to find the Km because I almost kind of alluded to that's what I was drawing here, but we can't do that. Cooperative enzymes do not obey Michaelis-Menten kinetics, and therefore we cannot estimate the Km of substrate for enzyme. You can call it that if you want. It's a value, but it's certainly not going to be the affinity. Okay. And so let's go over again why this is advantageous. To cover that, they're showing you in red a curve corresponding to velocity versus substrate for a highly cooperative enzyme, rod of S shape, versus an enzyme with the curve shown in blue that is non-cooperative. Okay? And what we want to do is we want to ask ourselves the question, what is the range, what is the difference in the substrate concentration that would enable us to observe a velocity that is 1/10 of Vmax versus 80% of Vmax? And actually, you know, it's kind of funny that they're doing it this way, right? Because in actuality, you know, calling this Vmax is dangerous, right? Because there is no such thing as Vmax for a cooperative enzyme. So we'll keep that in mind, and we'll give them a little bit of a break to make their point. But we'll remember that in this case, we're not talking about the Michaelis-Menten constant Vmax. So what they're showing me is that I will observe a ratio of 27 for the substrate concentration that's necessary to achieve a velocity that is 80% of maximal velocity over the substrate concentration that gets me 10% versus the cooperative enzyme, which in this case is a ratio of only 4. So the enzyme is responding to a much smaller change, a smaller change in the concentration of that substrate. And so this is ultimately the reason why we observe cooperative enzymes in cells, because there are going to be scenarios where substrate concentrations don't vary this much. You know, in the cell, they might vary by this much. Oops. Right, so in this scenario, if the substrate concentration plummets to 1 millimolar, it's down here, the cooperative enzyme is off. That substrate is now going to be left alone, and it can be used for other things that might be essential for the cell, which is easy to imagine once we start looking at chapter 15. You'll see that in our cells, the metabolic pathways get really complicated. There's a lot of sharing, right? There's a lot of crosstalk where substrates of one pathway are shared with multiple other pathways sometimes, right? And so that's why it's important that in this case, if the substrate concentration were to plummet in the cell to 1 millimolar, the cooperative enzyme doesn't touch that substrate anymore, whereas the non-cooperative enzyme with high affinity substrate binding will continue to catalyze the reaction until there's nothing left. It's cool, right? It's an innovative, evolution is innovative. Any questions? Yes, oh, no, I know that name. I know it's not William because that was my guess. Oh wait, you're Ethan. Okay.
So what does the ratio specifically mean? Is it just an easy number to compare?
Yeah, I mean, I could have said, what is the ratio of the substrate concentration that gets me to 90% of the maximal velocity compared to 5%? It's an arbitrary value that they chose, right? But what we really want to compare are extreme values. It wouldn't make sense to compare, say, 60% and 40%. We wanted, I mean, in my opinion, they should have done 90% and 10%. That would have been more symmetrical. But you would have gotten the same, roughly the same answer. Yep. All right. Okay, let's move on. 11 o'clock. Learning check. We even have time to do the learning check. An allosteric enzyme in the absence of substrate is 1,000 times more likely to be in the T state than in the R state. A mutation in the enzyme stabilizes the R state such that the T to R ratio is reversed. You would predict that A, the enzyme will not show cooperativity, B, the enzyme will show Michaelis-Menten kinetics, C, the enzyme will predominantly be in the R state. All the above or none of the above. let's just go through, let's go through one by one. So Leah is already backing, her money is on all the above. The enzyme will not show cooperativity. So why is this enzyme not going to show cooperativity, Leah? Because we're in the R state. You can't be cooperative if you start in the R state. You have to have two different conformations. One has weak affinity, one has high affinity. If you start in the high affinity one, then there's no possibility for cooperative ligand binding. So I agree with that. Then we go, the enzyme will show Michaelis-Menten kinetics. Why do you think that's true, Leah?
Because if we're not showing cooperativity, it's going to be a Michaelis-Menten curve.
Yeah, that's very lovely the way she said that. She said if it's not showing cooperative ligand binding, then it will obey the Michaelis-Menten model. And then the enzyme will predominantly be in the R state. Well, that makes complete sense because if the mutant stabilizes the R state, then that means that the enzyme will predominantly be in that conformation. So the answer was all the above. Very good. Now let's just briefly talk about allosteric effector binding. It's going to occur at the regulatory subunit site. And what's going to happen, is binding at that regulatory site, even though that binding is tens of angstroms away from the active sites, that binding is communicated to the active sites because of the structure of ATCase, right? That's why I showed you, to a large extent, the structures today. I wanted you to appreciate that the regulatory subunits are intimately connected to the catalytic subunits, such that changes in the conformation of the regulatory subunit are relayed all the way to the active site. And that's how this works. So binding of CTP to that regulatory subunit stabilizes the T state. How? By forming weak force interactions that stabilize the conformation of the regulatory subunit that are compatible with the T state conformation. In other words, the T state conformation has the lowest energy conformation. And to some extent, we can say why. We can say we're gaining additional weak force interactions between the T state of ATCase and CTP. And then they tell us that ATP is actually an effector, but it's a positive effector. It's the opposite of CTP. So you can see that instead of shifting the curve to the right, which I'll put in here, when you guys draw these curves in, make sure that eventually you get to maximum velocity, right? Because eventually substrate can overcome a negative effector. So in the presence of ATP, the curve shifts to the left. So that means that ATP is stabilizing the R state conformation as compared with CTP. That's really amazing to me because CTP and ATP are really similar. What's the difference between CTP and ATP? The base. Cytidine has one ring. Adenine has two rings. So somehow that regulatory subunit can still bind to the portions that are identical, the triphosphates and the sugar, but then that little minute difference in the bases is enough to tip the scales over. Where in one case, the interactions with cytidine stabilize the T state, whereas the interactions with adenine have the opposite effect. We can understand why, though. We know how to do this. We know that free energy changes can be related to equilibrium constants. And we know that the energy in this delta G naught prime comes from these favorable weak force interactions between the enzyme and, in this case, either the cytidine base or the adenine base. And that, and you know, just a few kilojoules per mole of energy, a few hydrogen bonds, can have a significant effect on the equilibrium. So one of the things, now that we're getting closer and closer to you guys being free of me, I want you guys to take away this notion that the molecular world is a balancing act of energy, right? And in some cases, the tipping point can be one hydrogen bond, right? And so it's this delicate balance that's going on, right? We have ATP in the cell, CTP is in the cell, aspartate is in the cell, right? All of these things, as their levels are going up and down, this amazing enzyme is exquisitely sensing the presence or absence of these things, the changes, and those changes in the energies of those interactions affect the equilibria, which then ultimately determines what these curves look like. Yeah?
Just out of curiosity, what about TTP and GTP? How will they affect?
I have no idea. It's an interesting question. You can do the experiment. Do it and let me know what you get. You can have my lab. All right, skip that one, and I now want to spend 8 minutes talking about phosphorylation, because it is, boy, is this important stuff. If those of you who are going to take Biochem 2 next semester, you'll see many, many examples where protein phosphorylation affects biological function. So in this case, there's going to be a protein that is going to be the acceptor of that phosphoryl group. There's going to be an enzyme called a protein kinase that will catalyze the transfer of a phosphoryl group from ATP to that protein, and typically it's an OH group on a serine, threonine, or a tyrosine residue, and this will be our product. And so we've already talked about this, right? I don't really need to go into it in a lot of detail. I really kind of went off when we first started talking about this a week ago, but I wanted you guys to appreciate that putting this phosphoryl group on a protein can really change things. Number one, a phosphoryl group is big. It's a sizable thing, right? So it can create steric interactions, which can be inhibitory, or it can form a binding site, you know, anything. And then I also pointed out that phosphoryl groups have negative charges. So this could potentially repel a substrate, or it could repel the binding of a protein partner. Or it could also stabilize the binding of the substrate. You can stabilize the binding of the partner. It can also induce conformational changes in the protein. You can imagine a scenario where you have, I'm going to draw Pac-Man. You guys probably don't know what that is. It's okay though. And so this is the conformation of Pac-Manase. And that's the most stable conformation. But then, actually, I'm going to change my model. I have a new model. So Pac-Manase is going to be like this. But then, I'm going to put a phosphoryl group here. And that phosphoryl group now, the way I've drawn it, is in steric conflict with the residues down there, as well as maybe those residues are asp and glue residues. So now I even have electrostatic repulsion. So now what's going to happen is Pac-Manase is going to open up, like I've drawn before, like this. So that's going to alleviate the steric conflict that was there. It's going to alleviate that electrostatic repulsion. And this is going to be what we would call the low energy conformation of protein, right? And again, that conformation could be active or inactive. We don't even know. That's why we do biochemistry, to figure these things out. So here's a real example. Already covered that. This slide is just showing that protein phosphorylation is reversible. So just as there are enzymes in our cells called protein kinases that catalyze phosphoryl transfer, there are also enzymes called protein phosphatases that will catalyze the hydrolysis of the protein, of the phosphorylated protein, returning it to the unphosphorylated form. Okay, so this is, I just wanted to spend a few minutes discussing this. This is a real example. So there is an enzyme called cyclic AMP kinase A, and it's involved in what's called the fight or flight response, right? So when you get a shot of endorphins, either artificially or if you are on an African savanna and running for your life from a tiger, or I don't think they have tigers, they have lions. This is part of the molecular pathway that's going to result in that. Now, normally you want this thing off. I only want to do this when, I really need to get going, right? And so, how do you inhibit the enzyme? Well, the catalytic subunit is normally bound to a regulatory subunit that inhibits the active site. It blocks the active site from being able to bind to substrate. And so what ends up happening is that during this fight or flight response, so I'm on the savanna, I'm having lunch, all of a sudden these cute little lion ears appear above the grass, and I'm like, okay, I need to run really fast, or I'm going to die. My body is going to make this molecule, cyclic AMP. We don't need to worry about that. That's Biochemistry stuff, by the way. Then what's going to happen is the cyclic AMP will bind to the regulatory subunit, induce a conformational change in that regulatory subunit through the mechanisms that we've been discussing all semester long now. So the cyclic AMP bound conformation of the regulatory subunit is now more favorable in this conformation that no longer can bind to the kinase catalytic domain, freeing it from the inhibitor, and now the kinase is active to do its thing in the cell. And that's it. So hopefully you guys are now really starting to appreciate that a lot of the biology is driven by molecular events that are a result of conformational changes that occur in proteins. And so as we now jump into the final 4 chapters, woohoo, of metabolism, I want all of you to try to employ that knowledge in thinking about all the examples that we're going to be talking about from that perspective. So see you at office hours.